All right, in this tutorial what we're going to do is we're going to start diving into some econometric modeling in SAS. Again, this is not an econometrics tutorial, nor is it a finance tutorial. It's a SAS tutorial, and so I'm not going to really be answering any interesting econometric questions as much as I'm just going to be using some of the procedure statements that SAS has to estimate some econometric models. And so just a heads up, we're not going to do anything groundbreaking here econometrically. What we'll do in this particular tutorial is we'll estimate cross-sectional. We'll cover cross-sectional regression analysis. We'll start at the basic OLS regression. Then we'll add some wrinkles that account for robustness in the standard errors. We'll account for maybe truncation in the dependent variable, and maybe we'll do some limited dependent variable stuff here. In subsequent tutorials, what I'll do is I'll cover panel regression, or what we call longitudinal regression, where we can account for random or fixed effects, and then maybe we'll even do some time series regression analysis a little bit later. But what we have here, you'll recall from the previous tutorial, we've put together some cross-sectional data. Okay, let me just explain what this is. Cross-sectional data here is, I'm going to run this and pull this new data set in. This data set is the average bid-ask spread for each stock in 2018 across every day. Again, I've calculated the average spread, the average share turnover, which is the ratio between trading volume and shares outstanding, the average market cap, the average stock price, the average trading volume, the average range volatility. Recall that this range volatility takes the difference between the natural log of the highest price during the day minus the natural log of the lowest price. So it measures the range, the price range during the trading day. This has been found in a early 2000 Journal of Finance article to be a good approximation for stochastic volatility. And then in the previous tutorial, what I did is I calculated the standard deviation of daily returns for each stock across each day in 2018, and that's this measure. So this is the more traditional measure of volatility, the standard deviation of daily returns. Okay, a couple of things here. Note something. That here, row 15, this is Apple. Notice that Apple's average market capitalization during 2018 was $922 billion. Okay, watch, if I do something here, if I take Proc Univariate, this is a procedure in SAS that tells me the distribution of some variables. If I take Proc Univariate of market cap, a couple of things are interesting here. First, it shows me the distribution, how the distribution looks here. Notice also, when I come up here to the simple statistics, the average stock in our sample has an average market cap of $4.8 billion. But the median stock only has a market cap of about $400 million. Notice that the skewness on market cap and the kurtosis on market cap are huge. There are some super large stocks that are outliers. So what we may want to do is we may want to account for the functional form. Again, this isn't an econometrics tutorial, so I'm not going to talk about how to find the proper functional form of each variable, but look, what we're going to do here is I'm going to say, I'm going to create a variable called log cap equals the natural log of market capitalization. And when I rerun the Proc Univariate, you're going to see that what am I doing here? I'm going to rerun the Proc Univariate now for the natural log of market capitalization. Let's see if that normalizes the variable a bit. Okay, there's the distribution for log of market cap. Look at what happened here. When I take the log of market cap, the mean and the median almost line up perfectly. The skewness is almost zero. So it did a very good job in normalizing the distribution of market cap. I might try to create nonlinear measures of other variables. For instance, in a 1992 Journal of Finance article, McKinnish and Wood, they took the square root of price as the functional form of price. So the purpose is not to argue whether or not that's a good idea or a bad idea, but it's just to show you that there are formulas that you can use inside of a data step to manipulate the variables. I might say that turn percent is going to be the share turnover as a percent. Remember, share turnover is the ratio of trading volume to total shares outstanding. If I times that by 100, I put that in percent. So this is just the purpose of what I'm doing here is just to show you within inside of a data step, you can manipulate some of the variables, maybe to normalize the variables. What I'm going to do after I've created these new variables, there's the 3 new variables I've created, is I'm going to start with simple OLS. Okay, the SAS procedure is called Proc Reg, data equals data 2. And what I want to do is I want to model bid-ask spread as a function of share turnover, right? The more trading volume that there is in a particular stock, the lower the bid-ask spread. So the coefficient on this variable should be negative. Again, this isn't an econometrics tutorial, and we're not doing anything very interesting here, but this is just showing you how to run some econometric models. Let's include the log of market cap, the square root of price, and let's include our volatility measures. Okay. Now I want to show you what happens here. So if I run proc reg with this model statement, it's going to generate an output, but before it does, it gives me a visual of the coefficients on this, the residual by regressors for bid-ask spreads. That's nice to see. If you're a visual learner, that's great. What's important, however, to note is that some of these plots take up a whole bunch of space on your computer and can slow down your computer. And so what I'm going to do here is I'm going to explain the parameter estimates and the output here, and then I'm going to show you how to hide those plots so it doesn't take up so much time and space on your computer. So here we go. Look, as you can see, the coefficient on turnover as a percent is negative and highly significant. That means the more trading volume in a particular stock, the narrower the bid-ask spread. That makes intuitive sense. Notice that small cap stocks have larger bid-ask spreads than larger cap stocks. That's also intuitive and has been found in the prior work, prior research. The square root of price, notice that thing is very close to 0. The t statistic is only 1.36. Again, this isn't a statistics tutorial, but I'm 1 minus the p-value confident that that particular coefficient is different than 0. So I'm only 82% confident that that coefficient is different than 0. Look, range volatility and standard deviation of daily returns, these things load positively on bid-ask spreads. This is also intuitive. The more risky the bid-ask spread, or I'm sorry, the more risky the stock, the more volatile the stock, the wider the bid-ask spread. This has also been shown in prior literature. So look, this is how we find how we run a regression and find coefficients from OLS regressions. What I want to do next is show you how to hide those graphics so it doesn't take up so much space on your computer. All I have to do is inside proc reg data equals data 2 say plots equals none. When I run that again, notice that it didn't print out the graphic, which will save you some time. Notice also that part of the output, it reports the root mean squared error, the r squared, the adjusted r squared. It also tells me that I'm missing 6 observations. That might be important. You need to be careful. I'm not exactly sure which variables are missing here, but there might be some variables missing. Perhaps there are some stocks that had 0 turnover, or some stocks that didn't report high prices or something like that, and that's why I'm missing some variables. So of the 7,954 stocks in the sample, this regression was only run for 7,948. That's important to note. Let's add some wrinkles here. What I'm going to do is I'm going to copy and paste this. And what I'm going to do is I'm going to account for the possibility that there is heteroscedasticity in the standard errors. For those of you who don't understand what I just said, you can learn about this by taking an econometrics class. Halbert White in a 1980 Econometrica article basically showed us how to correct the standard errors to allow for conditional heteroscedasticity, which is an important assumption when using OLS. All I have to do is, after my model statement, hit / and type white. Notice that it populates blue, which means that it's an important formula for this procedure statement, proc reg. When I run this, Notice what happens here. It doesn't do anything to my parameter estimates. All it did was correct my standard errors. Okay, and notice a couple of things here. My standard error for turn percentage got bigger. Right? My standard error for log of market cap also got bigger. Right? So when I control for conditional heteroscedasticity, that affects my the statistical inferences that I'm able to make. Notice also, look, before we controlled for conditional heteroscedasticity, square root of price was not significant. The t-stat was 1.36. After we control for heteroscedasticity, the t-stat increases to 3.05. I become more confident that that coefficient is statistically different than 0. And again, I don't find much of a change in the standard errors of range volatility and standard deviation of daily returns. So again, this is a way to be a little bit more robust when conducting cross-sectional regression analysis using OLS. Let me talk about the dependent variable here. The dependent variable is bid-ask spread, which is the percentage spread. It's bound between 0 and 1. In fact, if I look at the distribution of the bid-ask spread, we can make some important inferences while we're conducting cross-sectional regression analysis. Notice that it's bound between 0 and 1, and notice that a lot of the bid-ask spreads are very small and are censored around 0, right? So a couple of things that we can do here. We can say we can run another type of regression. So this is called, we can account for the truncation of the dependent variable at 0, or the censoring at 0, by running proc qlim data equals data 2. Okay, I'm going to include my model statement. And then what I'm going to do is I'm going to specify an endogenous variable. I'm going to say endogenous variable is my dependent variable. I'm going to say tilde, and it's truncated with a lower bound equal to 0. Okay, so say you're running cross-sectional data and you have a variable that's truncated. You can think of this as a one-tailed Probit model. And when I run this one-tailed Probit model, again, I didn't say plots equals none. Notice what happens here. My coefficients change, right? Notice that the sign of the coefficient on the square root of price flips and becomes significant when I account for the truncation of the dependent variable. This is important to understand. Some other factors. Look, the coefficient on share turnover and market cap, they're still negative and highly significant. The coefficients on volatility are both positive and highly significant, but that coefficient on the square root of price flipped signs and became significant, suggesting that this truncation might matter a little bit. Again, what I'm doing is I'm showing you SAS procedures that might help you be more robust when running some cross-sectional regression analysis. You can also say that if it's truncated between 0, it's also truncated. There's an upper bound of 1. Let's see if that has any effect on what we just ran. Notice that when I account for the truncation of the upper bound, the coefficient on square root of price goes positive again. In fact, this looks a lot like our OLS, our main OLS results. Okay, so you can account for truncation. You can account for censoring using the proc qlim functions. Let me copy. I'm going to copy Control-C and Control-V, copy paste that guy. And instead of censoring, or instead of truncating the variable, I can say that a lot of those bid-ask spreads are close to 0, but it still looks like that variable is continuous and isn't truncated. So I can estimate this censored regression with a lower bound of 0. Right, and that looks a lot like my OLS results, so it doesn't appear to affect my OLS results. So it seems like my OLS results might be fairly robust to censoring. SAS has a procedure called Proc that allows you to account for what we call Probit models, either one-tailed or two-tailed Probit models that account for truncation, or censored regression analysis. Okay. Let's do something else here. Let's say data equals data 3, set data 2. And what I want to do here is I want to create a dummy variable. Okay, so I'm going to write an if-then statement. Before I do, let me run Proc Univariate data 2 for the bid-ask spread. And let's look at that median right there. So we have a median bid-ask spread that is equal to 0.001739. So I'm going to create a dummy variable, and I'm going to say if spread is greater than 0.00173918, then high spread equals 1, else high spread equals 0. So I created a dummy variable. Okay. Again, this isn't telling us anything very interesting, but what I want to do is I want to show you how to estimate logistic regressions or Probit models with limited dependent variables or a dummy variable on the left-hand side of the equation. So when I run this, you can see that now I have a variable called high spread, which is 0 for any spread that's below the median, 1 for any spread above the median. What I can do, look, to estimate a linear probability model, I'm just going to copy and paste that with white robust standard errors. So if I estimate this equation with a dependent variable as my that is a dummy variable, right? This is called a linear probability model. Notice I made a mistake there and I said data equals data 2 instead of data equals data 3 where I created my dummy variable. Look at what happens. The variables all change, right? I got to be very careful here because my dependent variable is bound between is either 0 or 1, and the OLS assumptions require that the variable is continuous. Okay, so this is not a great regression that I should run. Instead, what I'm going to do is I'm going to estimate a Probit model or a logit model. I can do that in various ways. One way to do that is by proc logistic data 3. Now it's important here, if I just say proc logistic, this is a SAS procedure that allows me to estimate or account for the indicator variable as my dependent variable. But notice something, when I run this proc logistic model, what's going to happen is it's going to have all of my zeros first and all of my ones last. So what I have to do is I have to type in descending here. My model statement is going to be the same. I'm going to copy and paste this again. Okay. And if I run this, this is going to give me a logit, estimate a logit model using a dependent variable that is a binary variable. Okay. It uses maximum likelihood to estimate these things. There are my coefficient estimates under the logit model. There it will give me some inclination about whether or not these things are significant. It gives me the odds ratio estimates. For those econometricians, they'll understand this. I might also want to estimate using proc logistic a Probit model, which basically assumes a different distribution for the dependent or for the error term here. So what I'm going to say is I'm going to put a / link equals Probit. And so instead of a logit model, I'm estimating a Probit model with a dependent variable that is binary. And here's my Probit model. The coefficients vary slightly. Okay. Anyway, and it reports the standard errors of the coefficients as well. Again, it uses maximum likelihood as its estimation procedure. So SAS here, using proc logistic, is able to estimate a logit model or a Probit model. logit model. If you don't put link equals probit, the logit model is the default. If you say link equals probit, it changes the distribution of the error term, and that will give you the probit model. So anyway, hopefully that's helpful. Again, this is cross-sectional analysis. In the next tutorial, we'll do some panel data analysis.